Greetings. Okay, this problem has states the following. Water is pumped into a tank at a rate modeled by W of t equals that particular exponential function, liters per hour for time from 0 to 8. Time is measured in hours. Water is being removed from the tank at a rate modeled by R of t, where R of t is given by the chart. R is differentiable and decreasing on 0 to 8, and R is provided. At time equals 0, there are 50,000 liters of water in the tank. So the first part of the problem asks us to estimate R prime of 2. So they want to know the rate of change at time equals 2. The rate of change of R prime. The rate of change of R. So R prime of 2 be estimated by finding the slope of the secant line between 1 and 3. So the answer to part A would be that R prime of 2, the derivative of R at 2, is approximately equal to the average rate of change for R between 1 and 3. So that would be R of 3 minus R of 1 over 3 minus 1. R of 3 is 950. R of 1 is 1190. And that's over 2. And therefore, 950 minus 1190 divided by 2 yields negative 120. And since the units here are liters per hour, this will be liters per hour squared, because the units in the numerator are liters per hour from R, and the units in the bottom are time, which is another set of hours. Okay, so that's how we would do part A. Part B asks for us to use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. So water is being removed according to the chart. The chart has some intervals in there. It has an interval from 0 to 1. It has an interval from 1 to 3. And it has an interval from 3 to 6. And an interval from 6 to 8. The problem asks us to use a left Riemann sum with these 4 subintervals. So the length of this interval is 1, the length of this interval is 2, the length of this interval is 3, and from 6 to 8 is a length of 2. Using a left Riemann sum means to use the left endpoint of the interval to get the height of the rectangle. So in the first case, that would be R of 0, 1340. In the second case, it would be R of 1, which is 1190. On 3 to 6, it would be R of 3, which is 950. And then on 6 to 8, it would be R of 6, which is 740. So the Riemann sum would be this sum, which is 1 times 1340 plus 2 times 1190 plus 3 times 950 plus 2 times 740 for a total of 8,050. 8,050, and since we're adding up liters per hour times hours, this would be 8050 liters. So this would be the amount of water removed from the tank over the first 8 hours. Since R was said to be decreasing, a decreasing function has left endpoints, left Riemann sums that overestimate. So we would say that this is an overestimate. It is an overestimate since R is decreasing. Okay. For part C, the problem says to use the answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of the 8 hours. So remember, at time equals 0, there was already 50,000 liters in the tank, right? So that's where we're beginning. Add. The water is being pumped in at the W of t rate. So we're going to have to add on the integral from 0 to 8 of the W function, which is 2,000 e to the negative t squared over 20 with respect to t, and then we have to subtract off how much was being taken out. So how much was being taken out is what we found in part C, was how much was removed. So we're going to have to subtract off approximately 8,050. So breaking out the calculator yet again, 50,000 plus an integral from 0 to 8 of 2,000 e to the negative x squared over 20 with respect to x, and then subtract off the amount that was removed from part C, which is 8050, which gets us to an answer of 49786.195 liters. It does ask us to round to the nearest liter, so we would leave this as 49786 liters following the command of the problem. Okay, so for part D, is there a time at which the rate of the water being pumped into the tank is the same as the rate at which it is being removed from the tank? Why or why not? Well, for that problem, let's try to aim towards an intermediate value theorem. So we know at time equals 0, if we were to take the rate at which water is being pumped in, that would be W of t, and the rate at which it's leaving is R of t. So at time equals 0, W of 0 minus R of 0 would be equal to 2,000 e to the negative 0 squared over 20 minus 1340, which would be equal to 2,000 minus 1340, which is 660. At the end of the interval, at time equals 8, we know that W of 8 minus R of 8 would be equal to 2,000 e to the negative 8 squared over 20 minus 700. And that's going to be 2,000 e to the negative 8 squared over 20 minus 700. And this is negative 618.476. So, since both W and R are continuous, we have a value that's positive here, 660, and here we have a value that's negative. So by the IVT, we know there is a time between 0 and 8 when W of C minus R of C must be equal to 0. Thus, at that time, we see W of C equals R of C. So the answer is yes, and justification is by the intermediate value theorem.